Welcome back. So this is lecture 27 in this course on Bayesian modeling. My name is Himanshu Yadav, and the topic of today's lecture is analytical methods of estimating posterior distribution. Right. So in the previous lecture, we talked about different methods that we use in the Bayesian framework to estimate model parameters. Right. So the first method that we saw was analytical method of deriving the posterior distribution, and that's what we will talk about in today's lecture. Okay. You are collecting data in an experiment and you assume that ith observation, ith outcome in your experiment comes from an underlying probability distribution function f of x theta. So this is the underlying generative process you have assumed, okay, where theta is a parameter of this underlying generative process. And about theta, you make a prior assumption that theta has this distribution p of theta. Okay, so this makes your model. This is your likelihood assumption about what is the underlying process behind your data, and this is your prior assumption. So your assumption or your belief about the parameter before even seeing any data. Right? So this is your model. Now, as I discussed in the previous lecture, that in order to calculate the posterior, what you require is, so let's say x obs is the observed data. So in order to calculate the posterior, you need to multiply likelihood and prior and divide it by marginal likelihood, which is integration of the likelihood and prior with respect to theta. So this is what you need to do if you want to analytically figure out that what would be the posterior distribution. Right? If you are able to do this integration, so some of the functions won't be even integratable. Okay, if you are able to do this integration, basically you are able to find out what will be this constant, and you multiply these two. Okay, and as a result, if you get a function which denotes some proper probability distribution, let's say g of theta, okay, then you can say that your posterior distribution would be g of theta. Okay, if you are able to solve all this and you get a proper probability distribution g of theta. Okay, and then you have no problem, because what you will need to do, you will need to draw samples from your posterior density. Okay, and now you can easily draw samples from g of theta. Okay, but the problem is that integrating this likelihood into prior is not straightforward. In fact, most of the functions won't be integratable, right? When you multiply likelihood and a different kind of prior. And it's not always the case that you will get a proper probability distribution g of theta. Okay, so you might end up getting some function which is your likelihood into prior, okay, some function which could be an exponential function or something, but it may not be a proper probability distribution. So for example, it may not be a beta distribution or a gamma distribution or a normal distribution, right? So standard probability distribution that you know of. So it could be some distribution, but not a proper probability distribution from which you can do sampling, right? So that defeats our purpose. So if you cannot get a proper probability distribution, then you are facing the same problem, that how do you do sampling from this, right? So it does not give you an analytical solution, right? So there would be only a handful of cases where you can get a proper probability distribution g of theta. When you solve this, you can get a proper probability distribution g of theta. There will be only handful of cases, okay, and those are the cases of conjugate priors. So in cases of conjugate priors, you will be able to get a proper probability distribution as your posterior. So in these cases, you will be able to analytically derive your posterior distribution. Okay, so when you are choosing conjugate priors, you can analytically derive the posterior. Okay, so conjugate priors are the priors on the parameters which make it possible for that particular likelihood to calculate the posterior analytically. So what are those cases? We discussed a few cases. For example, if you have a binomial likelihood, then beta prior on the parameter theta, on the parameter probability of success, is a case of conjugate prior. Okay. For example, if xi comes from binomial theta and theta comes from beta alpha beta, then the posterior distribution of theta given some data x obs is given by a beta distribution, where the first shape parameter would be alpha plus summation of observed data points and beta plus n minus observed data point and its summation, something like this. Okay. So, this is a case of conjugate priors for the binomial likelihood. So, when you binomial likelihood and if you choose a beta prior on theta, only then you can derive this. If you have a normal prior on theta, then you cannot derive this. Then it won't be possible to integrate this likelihood into prior. Another case was Poisson gamma. So, when you have Poisson likelihood with underlying parameter lambda, and on lambda if you have gamma prior with shape parameters, let us say alpha beta, in that case your posterior distribution of lambda given the data will be a gamma distribution with parameters alpha plus summation x obs and beta plus n, okay, where n is the number of data points. So, we discussed couple of examples, there are more. Okay. So, there are, for example, for normal likelihood, if you have a normal likelihood with non-variance, then a normal prior on mu is a conjugate prior. So, if you have, let us say xi comes from normal mu and sigma is fixed, let us say sigma is sigma naught, then if you choose a normal prior on mu, let us say normal a b, okay, then mu, so basically posterior distribution of mu would be a normal distribution, okay, with certain mean and variance, right. So, it is not important here. So, you can analytically derive the posterior distribution of mu in this case as well, okay. So, these are the cases, basically cases of conjugate priors where you can analytically derive the posterior distribution of your parameters of interest, okay. Let us take one example and see how it works, okay. So, let us take an example where we try to analytically derive posterior distribution, okay. So, we can take beta binomial example. So, let us say you assume a binomial likelihood. So, let us say outcome in the ith trial of your experiment comes from a binomial distribution with underlying probability of success theta, okay, where on theta you assume a beta prior with shape parameters, let us say alpha and beta. These are two shape parameters of a beta distribution, okay. So, let us try to derive the posterior distribution of theta given the observed data x1 to n. So, x1, x2, x3 and up to xn. Let us say these are the observed data across n experiments or something. And let us say one more information that you need is that sample size in each experiment, capital N. So, capital N is the sample size in each experiment. So, n is the total number of trial in the experiment, xi is indicating ith experiment. So, how many correct responses or successes you will get out of total n trials in ith experiment when it comes from a binomial distribution, right. So, in order to do this, you need to multiply the likelihood given x1 to n given the data prior density of theta divided by integration of likelihood and prior on theta with respect to theta, okay. And this integration should go for from 0 to 1 because that is the range of parameter theta, okay? That is the parameter space from 0 to 1, theta can take any value between 0 and 1, okay. So, let us try to solve this. So, what is the likelihood? What will be the likelihood of theta given this data, given that the likelihood assumption is that it's a binomial, that the underlying process is binomial. So what is the PDF of binomial distribution? N chooses X. So basically n factorial, n is the total number of experiments. Not the total number of experiments, but here n is sample size, the number of trials in each experiment. N chooses X divided by X I factorial. Okay, Xi is the number of observed successes in ith experiment. Okay, so let me write it only for first one. So let's say x1 factorial, and let's write this one as n1 or maybe n. Let's say n is same across all experiments. All experiments are of same sample size. So x1 factorial. So this is our first experiment. Or you can maybe write L of theta given x1. So data from first experiment. So x1 factorial and n minus x1 factorial. And here theta to the power x1, 1 minus theta to the power n minus x1. Okay. So this is likelihood of observing x1. So the first data from first experiment. Similarly, you can get it for x2, data from second experiment. So this would be n factorial divided by x2 factorial, n minus x2 factorial, theta to the power x2, 1 minus theta to the power n minus x2. Right? If you do this up to L theta given xn for x1 to xn, so through all experiments, then this would be n factorial xn factorial n minus xn factorial theta to the power xn 1 minus theta to the power n minus xn. Xn is the number of successes in the nth experiment. Okay. So in order to calculate joint likelihood, so what is the likelihood for a particular value of theta given data from all these experiments x1 to xn, from 1 to n, given all these data, it would be product of all these likelihoods. So it would be basically product of each likelihood, because we want to calculate likelihood of joint occurrence of all these data from x1 to xn. Okay. Why do we do this, by the way? In order to calculate joint likelihood, why do we take this product? This is because of, do you remember the conditional probability formula? What was conditional probability formula? Probability of any event A given B is given by probability of A intersection B. So probability of joint occurrence of A and B divided by probability of B. Okay. What will happen if A and B are independent? So if you are given A and B are independent, then what will happen? In that case, you can say P of A given B will be equal to P of A, because probability of A does not depend on B. So it will be just probability equal to probability of A. So in this situation, you can rewrite this conditional probability formula as probability of A equals to probability of A intersection B divided by probability of B. So probability of A intersection B is just then probability of A into probability of B. So probability of joint occurrence of A and B when A and B are independent is basically probability of A into probability of B. So basically product of their individual probabilities. Okay. So that's the idea we are applying here in calculating these joint likelihoods. Right. So we are calculating the joint likelihood of any parameter value given data points from x1 to xn. Okay. And it would be likelihood of joint occurrence of x1 to x1 given any particular value of the parameter theta. Okay. So that would be assuming, and this is a reasonable assumption to make here, that all these experiments x1 to xn, x1, x2, x3, all these experiments are independent of each other. Okay. So if these experiments or data points are independent of each other, then you can say that this thing will be product, that this thing will be product across, this thing will be product of all the individual likelihoods. So, likelihood of x1, likelihood of x2 and so on, right. So, from I equals to 1 to n, it will be product of likelihood of theta given xi, right. This is something we have calculated above, right, here for each of them. Okay. So, basically then joint likelihood would become multiplication of all these terms. So, how do we take product of all these terms? So, basically what will happen, it would be n factorial to the power n divided by x1 factorial into x2 factorial and so on xn factorial. Similarly, n minus x1 factorial. Okay, so you can write it in a compressed form like this. So, basically it's product of I is equals to 1 to n xi factorial and product of I is equal I 1 to n of n minus xi factorial. Okay. And then here it is theta to the power, see. So, in theta term what you have, theta to the power x1, theta to the power x2. If you multiply all of them, what will happen? Because these are exponents of theta, so they will get added, theta to the power x1 plus x2 xn, like this. Similarly, 1 minus theta to the power will also get added, n minus x1 plus n minus x2, so on, right. So, you can rewrite it in a simpler form like this, ni to the power n product of xi factorial, product of n minus xi factorial, okay. Then theta to the power summation xi 1 minus theta to the power summation n minus xi, and the summation is from I is equals to 1 to n. Okay. So, this is the likelihood. So, so far we just derived the likelihood function of theta. What would be prior density? What would be prior density of theta? So, prior density that we have chosen here is a beta distribution, right. So, what is the PDF of a beta distribution? So, this is the PDF of a beta distribution, alpha minus 1 factorial, beta minus 1 factorial divided by alpha plus beta minus 1, x to the power alpha minus 1, 1 minus x to the power beta minus 1. But here the random variable x is actually theta, not x anymore, right. So, because we are setting up this beta distribution on theta. So, what we are saying in our prior statement, in our prior assumption statement, that theta comes from beta alpha beta. Okay. So, basically what we are interested in is in prior distribution of theta given these parameters alpha and beta, okay. So, which we are saying is a beta distribution. So, this random variable theta has a beta distribution. So, let us write what will be the PDF of theta. Okay. So, PDF can be written as alpha minus 1 factorial, beta minus 1 factorial divided by alpha plus beta minus 1 factorial, then x to the power alpha. Here what is x? What is the random variable? Theta. So, theta to the power alpha, alpha or alpha minus 1, alpha minus 1, right. So, theta to the power alpha minus 1 and 1 minus theta to the power beta minus 1. So, that is your prior density. Okay. So, what will happen if you multiply this term and this term? Okay. So, let us ignore this constant for now, because this will just depend on these constants alpha, beta, and in this case the data that you have. Okay. So, let us get the kernel of the function. When you multiply them, what will happen? So, if you multiply this and this, right. So, likelihood into prior, what you will get is this, that theta to the power, so some constant, let us say k, into theta to the power this plus this. If you multiply them, then these exponents will get added. So it would be theta to the power alpha plus summation xi up to n from 1 to n minus 1. So you have alpha minus 1 here, alpha minus 1 plus this term summation of x, and 1 minus theta to the power beta plus summation n minus xi minus 1. Okay. So let me write 1 minus theta term here. So into 1 minus theta beta plus summation n minus xi up to n minus 1. Okay, so this is the kernel we get of likelihood and prior. Everything else is constant, so you will have to just calculate it. If you integrate this, you will get another constant. So everything here will remain some constant that would ensure that the area under the curve is equal to 1. But this is the main term. So basically, this is the function of theta. Okay, theta and all these other things, right? So this thing is function of theta. Right? So what you are getting is basically this k into theta to the power alpha plus summation xi minus 1 and 1 minus theta to the power beta plus summation n minus xi minus 1. Okay. This term is actually same. Basically what it is showing you is that it is the kernel of a beta distribution whose shape parameters are alpha plus summation xi and beta plus summation n minus xi. See, this is of the same form. So if you have, let's say, a beta distribution with these parameters, with these shape parameters, alpha plus summation xi, beta plus summation n minus xi, then what would be its PDF? And let's say this is a distribution for theta. So its PDF would be something like this: theta to the power alpha plus summation xi minus 1, 1 minus theta to the power beta plus summation n minus xi minus 1. This is exactly what we are getting here. Okay. So when you multiply a binomial likelihood and a beta prior, you get a beta distribution with these shape parameters, which is alpha plus summation of xi, beta plus summation of n minus xi. Okay. So this is how you can analytically derive the posterior for conjugate cases. I haven't done the full derivation, which you can try at home if you know how to do integrations and all that. I'm not going to go into all that detail, but this is just to show you that if we just look at theta terms, we are getting a kernel of a beta distribution. Okay. Let us take this example quickly in R and see how it would work, how the analytically derived posterior would look in R. Okay. So suppose you did an experiment where you are recording number of correct responses, and you did such 5 experiments. Okay, and these are the data points. Okay, so you did 5 experiments. In each experiment, sample size, so number of total trials is, let's say, 50. In the first experiment, you observed, or you can think of it like this: you toss a coin 50 times and you repeat this 50 coin toss experiment 5 times. Okay, so how many heads you observe, right? Or let's say you are giving a word recognition task where people have to recognize whether word is a word or non-word, whether it's string or word or non-word. Then we are recording number of correct responses. So let's say first time 45 responses were correct, second time let's say 40, third time let's say it was 39, fourth time let's say 47, and then let's say 48. Okay, so this is the observed data. Okay, and what you assume is that each observed data point comes from a binomial distribution with underlying parameter theta. Okay, where theta has a beta distribution with underlying alpha and beta as 90 and 10, right? So I will write it as A and B. Okay, where A is equals to 90, B is equals to 10. So these are basically shape parameters of your beta prior. Okay. So let us first derive the analytical posterior, and then let us derive posterior using method that we already know, using grid approximation method that we have done in previous lectures, and let us compare them. Okay. So first I will derive analytical posterior. So analytical posterior would look like this. So if theta comes from a beta distribution, then theta given the observed data will come from a beta distribution with parameters A plus summation of observed data points and B plus summation of n minus observed data point. So this will give me my posterior. Okay. So now I know the posterior. So I can, what I can do, I can directly sample from the posterior. So posterior samples. So I just need to draw now samples from a beta distribution. I know exactly what distribution is the posterior distribution, right? So I just need to use R beta, and first shape parameter would be A plus summation of observed data. Second shape parameter would be B plus n minus summation of n minus observed data. Okay. How many samples do you want? So let's say we collect 4,000 samples. Okay, or 5. Okay, 4,000 is fine. So we collect 4,000 samples from this. And let us see a histogram of these posterior samples. And this is how it looks like. So this is the posterior distribution of theta given these data and given your prior assumption. Okay. Now let us try to do the same using grid approximation approach that you have learned already. So what you do in this approach, you sample a lot of values of theta from its from a, let's say, a uniform distribution. How many? Let's say 10,000 or something from 0, so between 0 and 1. Okay. Once you have 10,000 values of theta, for each of them you calculate likelihood. So what would be likelihood? D binom, observed data. Another thing you can do is sum of observed data into, and sample size would be now 50 into 5, and theta will be probability parameter will be theta, vector of theta. So this will give you likelihoods corresponding to each theta, and then prior will be d beta, okay, theta vector a b. Okay, so this would be likelihood and prior. So now you can calculate unnormalized posterior, which would be likelihood into prior, and then you can draw posterior samples based on grid approximation from your theta vector using sample function. How many samples you want? Let's say 4,000, and probability will be so basically weights will be a normalized posterior and posterior density, and replace equals to true. So this will give you posterior samples using grid approximation approach, okay, without analytical method. And this is how it looks like. Okay, so it seems to look slightly different from analytically derived posterior. Okay, so let us compare them. Let us see how close we are to the analytical posterior. Okay, so how do we compare them? Can use ggplot. So data frame, theta, posterior samples of theta are basically posterior samples using analytical approach, posterior samples using grid approximation, right? And then you can say method. So first one is analytical, and repeat this 4000 times, and the second one is grid approximation 4000 times. So now this is your data frame. Now we can draw, let's say, density plot or something. Okay, where color is method. So of course here you also need to give aesthetic x-axis is equals to theta. Okay, so this will work now. So let us see how do they look like side by side. So this is how they look like. See, the red one is analytically derived posterior. The blue one is posterior derived using grid approximation. You see, it behaves slightly weird, right? And that is precisely because you had just 10,000 samples, out of which many of were wasted. And when you are using the sample function, you are drawing from the same region, basically same range again and again. So that's why it might show very weird behavior. And this is not the only problem, especially when let's say the parameter space is too large, then it becomes really difficult. Then you might get very few samples on the posterior distribution. And if you get fewer samples from the non-zero posterior density region, then the posterior recovery will look bad. So you might get a weird shape of posterior, you might get multiple peaks, and all those problems can happen. Okay, but at least for this case, this is seems to be working, but there seems to be not a very good posterior recovery, especially in this region. Okay, but if you increase the number of grid points here, then this might get better. Okay, so let's see. Okay, see, so this is already better when you increase the grid points. Okay, so this is how we can analytically derive the posterior distribution, but this you can do only in cases of conjugate priors. But once you can analytically derive the posterior, then you don't need to anything. You just draw samples from the posterior distribution that you derived. In this case, we derived this posterior, beta posterior, and we directly draw samples from this. So this is very straightforward and computationally very, very efficient, right? But the problem is that in most cases, we won't be able to analytically derive our posterior, because in practice we do not use these conjugate prior cases. Okay, so in practice we would have much more complicated likelihood and non-conjugate priors. So in those cases you cannot use analytical method, you need to go with some computational method. Okay, and as we will see later on, that a simple computational method like grid approximation is not enough. So you need to come up with better computational methods. And that would be the topic of our discussion for next few lectures. We will be discussing different computational approaches and their limitations and pros and cons in computing the posterior distribution of a parameter of interest. So I will stop here. We'll meet in the next lecture. Thank you.